So far we know that by using the Kw equilibrium expression, we can get the concentrations of H3O plus and OH minus by rearranging this equation, because we know that Kw is equal to 1.0 times 10 to the negative 14, right? And this is going to allow us to assess whether or not a solution is acidic, basic, or neutral. But guess what, folks? The concentrations within all solutions vary a lot. And that means we can have negative numbers, we can have positive numbers, pretty much a whole slew of different types of concentration. So to make it less difficult and easier for calculations, what we do is we convert every number that we can find in chemical and biological systems to what we call a numerical p-scale. So that means if we have negative exponents, for example, of H3O plus concentration or OH minus concentration, we can convert that with the p-scale, and that just means taking the base log of 10, okay, and multiplying it by -1. And so p-scale is going to equal to negative log of whatever the concentration is, and it can be the concentration of H3O plus or OH minus. Since our focus is H3O plus and OH minus, we can say our p-scale of H3O plus is going to equal to negative log of whatever the H3O plus concentration is. Now for us, instead of writing P of H3O plus, we simply write pH. Okay, and of course we've seen the pH scale before in lab, and you might have seen it before in high school or whatever other courses you've taken, and of course in Chem 101. Well, now we're getting the details of where it all comes from, right, folks? And so we can write pH is equal to negative log of H3O plus. This is going to allow us to get a positive number instead of having to deal with anything negative. We also can do the same thing for the concentration of POH, so we'll just say POH is equal to negative log of the OH minus concentration. But of course, in our course, we normally focus on pH. We can also think of pH as the potential for H plus or H3O plus to be in a solution. So if it has a very, very small pH, then the potential for H3O plus to be in solution is very high, for example. And then for POH, we can look at it as the potential of OH minus being in a solution. And so if you have a very low OH minus, that means you're going to have a very high POH to signify that you have a very basic solution. And so we'll be able to get into details of the pH scale. We won't be able to get into a lot of details of POH. You can see that as you go further in chemistry courses. But for our course, a lot of focus, especially in the lab as well, is going to be that pH scale. So of course, let's go ahead and do a little mini example here. If I have an H3O plus concentration that's given to you, and say this concentration is 1.0 times 10 to the negative 12, and I say, okay, what is the pH? Then I would take this 1.0 times 10 to the negative 12, and of course, plug it into my pH calculation. So 1.0 times 10 to the negative 12, and that for my pH is going to equal 12. All right, folks? And so a lot of times when you're seeing a pH scale or something like that, and it's very ginormous estimates, we usually write it as simply 1 and 2, 12, right? But because we are dealing with logarithms, guess what, folks? That pH and POH value does have decimal places after it. The number of decimal places after it is going to depend on the number of significant figures that's given in the concentration. So in this H3O plus concentration, we're given 2 significant figures. Therefore, the decimal place after my pH number should be 2. So for example, my pH for this, instead of writing 12, will be 12.00. That would be the correct number. And when you're going to a lab and you actually use a pH meter or a potentiometer, you will see that it goes by 2 decimal places, because a lot of times our concentrations are 2 significant figures. Now, if your concentration is 3 significant figures, then you'll see 3 decimal places usually in your pH. Now let's start to layer information. So we have our Kw value. We know it's 1.0 times 10 to the negative 14. But we know also from our Rice table from before with auto ionization that the H3O plus and the OH minus concentration is equal to 1.0 times 10 to the negative 7 molar. And when the H3O plus and the OH minus concentration are equal, then that means we have a neutral solution at 25 degrees Celsius. So if we know the concentration of H3O plus and OH minus when it's neutral, we can get the pH and of course the POH for at those particular concentrations. So again, our focus is going to be pH. So pH is going to equal negative log of the 1.0 times 10 to the negative 7 molar. So therefore, my pH is going to equal 7.00. And so instead of simply just saying H3O plus and OH minus concentrations are equal, and therefore they equal to 1.0 times 10 to the negative 7, instead of using that number, we can simply also say that pH at 7.00 is also a neutral solution where the H3O plus and OH minus concentrations are equal. And so we kind of set our pH scale at 7 to represent neutral. Now we said earlier that H3O plus and OH minus concentrations, they vary. So to capture all those variations, we use the pH scale. Above 7, it goes up to 14. Below 7, it goes down to 0. Right, folks? And we use this to our advantage to help us understand what solutions are acidic or basic, and of course, to do calculation. Some examples will be like beer is very acidic, or household ammonia is very basic. You can also associate different pH items to the chemical Avengers. Like, of course, we saw NH3 Iron Man. NH3 is going to be ammonia. So you can say NH3 Iron Man is also basic and household ammonia as an example. And there is another scale, but instead of for pH, it will be for pOH. But our focus is going to be the pH scale specifically, okay? That does not mean we will not be doing pOH calculation. That does not mean that. It just means that when we're in lab and when you're getting a lot of different calculations, a lot of times, larger word problems, they will focus on pH. That's all it means. But you still should be able to get, but of course, you still can get the pOH as well, which is taking the negative log of 1.0 times 10 to the negative 7, which is still going to be 7.00. So both the pH and pOH scale still have 7 as the neutral solution here, okay? So we can start to consolidate information. We can say, okay, our pH scale is going to range from 0 to 14. At 7, pH of 7.00, we're going to have a neutral solution, pH of 7.00. And of course, at pH that's less than 7, so it can be literally 6.999 all the way down to 0, is going to be considered acidic, or a pH of less than 7. And then we're going to have anything that's over 7, 7.00001 or higher, right, is going to be considered basic. So pH that's greater than 7 is going to be considered basic. And a lot of folks might say, well, does this scale capture everything? It doesn't capture everything, but it effectively covers the spectrum of acid-base chemistry and biology for most of all of our courses that we take. So that's the reason why we use that here. We also see a trend as well. The higher the pH, the lower the H3O plus concentration. And why are we focused on H3O plus? Because that's what the H stands for. The H here is going to stand for H3O plus, or sometimes simply H plus. And so we see a little pattern when you have a very, very high pH, meaning it's very basic, you're going to have a low H3O plus concentration. And when you have a very, very low pH, right, you're going to have a high H3O plus concentration. And remember, just because it's basic doesn't mean you still won't have a little bit of H3O plus in solution. And just because it's acidic doesn't mean you won't have a small amount of OH minus in solution over here, because we know from the autoionization of water, that's one of the patterns that we see. We see the fact that both of these ions, H3O plus and OH minus, are in solution. And also, if we look at the scale and we say pH of 1, pH of 2, because we're dealing with the logarithmic base of 10, we can say that pH of 1 is going to be 10 times more acidic, for example, than pH of 2, which is going to be 100 times more acidic than pH of 3. And how am I getting that? Where I'm saying, okay, 10 to the 1 is going to give me 10 times. 10 to the 2 is going to give me 100 times. 10 to the 3 is going to be 1,000 times, et cetera, et cetera. And so by using our logarithmic base of 10, we're able to make relationships between the pH scale as well. And using this interpretation, we can go further. We take our pH expression, which is pH is equal to negative log of H3O plus, and then we take the anti-log of this, we can actually solve for H3O plus. And so therefore, my H3O plus concentration is equal to base 10 raised to a power of minus pH. And so we can actually use this to solve for H3O plus concentration when we only are given pH, for example, or we can also get the OH minus concentration if we have the pOH. It's the same thing. So if I want to find the OH minus concentration, I'll take 10, raise it to the negative power, whatever the pOH is. And so, of course, this is going to be very useful when it comes to calculations, right? So, for example, if I have a pH that equals to 5, and I need to find the H3O plus concentration, I can use this expression. I can say, okay, my H3O plus concentration is going to be 10 raised to a power of negative 5, because they gave me the pH here. And when I, in my calculator input 10 to the negative 5, I get 1.0 times 10 to the negative 5 molar, which therefore is my H3O plus concentration. And so again, you can use that to your advantage to be able to then make a relationship between H3O plus, pH, and even go further with KW. But let's go ahead and put this all together by relating pH, pOH, and KW together. Okay, it's layering information time, folks. So we have our KW value, our ion product concentration, or constant, sorry, and that's going to equal to our H3O plus concentration multiplied by our OH minus concentration, which we know is 1.0 times 10 to the negative 14. We can get our individual concentrations of H3O plus and OH minus, which we know is going to be 1.0 times 10 to the negative 7 molar for each. We also know that pH is equal to negative log of H3O plus and POH is equal to negative log of OH minus. We use that P scale to help us keep positive numbers and be able to get a scale, right? A pH scale. Now, of course, layering all this information is going to allow us to go a step further and create an expression that connects all the variables together. And that is going to allow us to use the P scale once again. So we already used the P scale for H3O plus and OH minus. And when you're taking negative logs and negative logs multiplying by one another, you end up adding them later on. So we can have this here as negative log of H3O plus, okay? And then plus negative log of our OH minus here. You can do that. All we need to do is use our P scale value for KW here and for 1.0 times 10 to the negative 14. So that means I'm going to have negative log of 1.0 times 10 to the negative 14 here. And then I'm going to have this is equal to negative log of KW. So again, essentially what I did is I want to get this entire expression and put it on the P scale as well. That's all I did. So I took the negative log of both sides. That means I'm going to have this KW value here is now going to be negative log of KW, which is simply going to simplify to PKW. Okay. This negative log of H3O plus is simply going to simplify to pH. Of course, we're going to add that to the negative log of OH minus, which is going to simplify to POH, which we already know. Okay. And this whole thing is equal to the negative log of 1.0 times 10 to the negative 14, which is simply going to be 14.00. So now we have a new expression that relates pH, POH, and PKW, or the KW value. So that means, folks, if I have my pH value, I can find H3O plus. If I have pH, I can find H3O plus. If I have OH minus, I can find POH. Well, now if I have pH, I can find POH, and then I can use POH to find my OH minus concentration. Or if I have H3O plus, I can find pH, and I can use pH to find my OH minus concentration. Either way, this is going to provide that relationship. So if you have to go and do extra work and calculations where you get the H3O plus concentration, and then you go further and get the pH, and then they ask you for POH, all you need to do is plug it into this overall expression here. Now again, our PKW value is equal to the 14.00, right? So instead of writing PKW, a lot of times you'll just see it written as pH plus POH is equal to 14.00. A lot of times you'll just simply see it be put as 14, okay? Either way to help us simplify the expression. And remember that pattern we saw with the auto ionization of water? We increase H3O plus, we decrease OH minus. We actually see those same patterns with pH and POH. So if you increase pH, you effectively decrease POH, right? So we're looking at our scale here, and this actually has the POH scale. We have our POH scale here, and we have our pH scale. We're going to focus on the 0 to 14 section. We're going to focus on the 0 to 14 section. So when our pH is 14, our POH is 0. Okay? And then when our pH is 0, our pH is 14. So again, the relationships are inverse to one another, which makes sense because H3O plus and OH minus are inverse of one another. So again, our focus is going to be pH scale, but this is an example of what the POH scale looks like. Now, outside of calculations, we can also obtain pH values from the lab itself. Now, we've seen a couple labs thus far, and we were able to use acid-base indicators, which are simply just organic substances that change color at specific pH. That helps us with titration. We're also able to get pH paper that are like impregnated with different organic species to show that color change as well. And then, of course, as we go further on, we're going to be able to do experiment 18, which is basically using a pH meter, and we'll be able to see the pH meter and get a value. And even if you can't see it here, this is like 10.13. You'll see the values are going to be 2 decimal places, like I was saying before, that you'll see with a lot of these pH meters. Okay? So one cool thing is when you're dealing with like acid-base indicators, you're going off of estimates. With the pH meter, you get to get a direct measurement, which helps with making things more quantifiable. All right, folks? So let's just keep that in mind too. After we kind of have seen all these relationships, the only thing left to do, folks, is some calculations. So back to the Avengers compound we go. Okay, so we are back. What is the first thing we need to do? Read the question, determine the variables, get the equations, and then come up with a strategy to approach it. So this says determine the POH. All right, what is POH? Automatically, I'm going to start writing POH is equal to negative log of whatever my OH minus concentration is. It says determine the POH of a solution with the OH minus concentration of 0.464 molar. So they already gave me the OH minus concentration here. Is 0.464 molar. Okay. And it says we're at 25 degrees Celsius, which is what we're used to seeing. We're able to use our KW value now because we know that. So that's going to help us there. Do we need to use the KW value? Well, so far we don't need to, but let's continue to read. It says, next, determine the pH. Well. So if we are able to relate pH and pOH, the only expression that's going to do that is that pH plus pOH is going to equal to pKW, which we know is 14.00. So did I have to go through and use my 1.0 times 10 to the negative 14 here? No, but I did have to get the negative log of that value and get my pKW as 14 and then use the overall expression here to connect pH and pOH. Okay, folks? So what is our plan? We have our equations. Now let's get to the nitty gritty. Well, first we want to calculate our pOH. Once we have our pOH, we want to solve for pH. And so I can basically rearrange this expression to solve for pH. If I subtract pOH from the other side, I can get my pH. So therefore, my pH is going to equal 14.00 minus whatever the pOH value is. And all I need to do is plug and chug at that point. So let's go ahead and get to it. First things first, my pOH is equal to negative log of 0.464 molar. That's what we have there. Now this pOH therefore is going to equal to 0.333. That's what I got in my calculator. The next we need to do is solve for pH. So a lot of times you'll just start with saying pH plus pOH is equal to 14. But again, we've already rearranged it here. So I know my pH is going to equal to 14.00 minus 0.333. When I do the math here in my calculator, I get 13.667 as my pH. Now, that means we've already answered the question, right? We got our pOH value, we got our pH value. As you can see, this pH value is 13.667. Does that make sense as far as decimal places? Well, we got to see what we were given. We were given 3 significant figures here for the OH minus concentration. So yes, it's definitely okay for us to have 3 decimal places here for our pH value. So this will be our answer here, and this will be our answer here. That's one way that we were able to connect our concentration of OH minus to pH. Okay, folks, of course, we're going to get way more examples once we add more layers of information, like when we get into more details about acids and bases specifically. So just hold your horses on that. Right now, just make sure you're understanding these details, and then we'll just keep on layering and layering. Okay, folks?